Now we're going to talk about the slopes of parametrized curves. So we're going to take slopes of parametric equations, basically. But we want to find dy dx, which is, of course, the slope, but we're going to do it parametrically. So if all three derivatives exist and dx dt doesn't equal 0, the derivative of y with respect to x is equal to dy dt over dx dt. And, of course, from a fractional standpoint, if you divide by dx dt, you're multiplying by dt over dx, and the dt's would cancel there. So it would be dy dx. So it looks like it's going to work out. And, of course, it does. So let's take a look. We want to find dy dx for the parametric curve x equals 3 sine of t, y equals 2 cosine of t. We know that dx dt, the derivative of x with respect to t, is going to be 3 cosine of t. The derivative of y with respect to t is simply going to be 2 times negative sine t, or negative 2 times the sine of t. So dy dx is going to be dy dt, which is negative 2 sine t, over dx dt, which is 3 cosine of t, which is negative 2/3 the tangent of t, because sine t over cosine t equals the tangent of t. Also, we can use Leibniz notation. Works out very nicely here. Dy dx equals dy dt times dt dx. Dy dx is equal to dy dt, which is negative 2 sine of t. And then we have it flipped, dt over dx, because now we're not dividing. We're just basically taking this, multiplying by the reciprocal. Dt over dx is another way of looking at it. And dt over dx is going to be the reciprocal of dx over dt, which is 3 cosine of t. The reciprocal is 1 over 3 cosine t. And you get negative 2 sine t over 3 cosine t. And, of course, that's negative 2/3 tangent of t the same way, no matter which way you look at it. All right, here we have an example. We're supposed to find the line tangent to the right hand of a hyperbola branch, and it's defined parametrically by x equals the secant of t and y equals the tangent of t. And here is the curve right here of this hyperbola. We're trying to find the tangent at the point radical to 1, and that's the point where t is pi over 4. So when you put a pi over 4 in for t here, x is going to be radical 2, and the tangent of pi over 4 is 1. What is the slope? The slope is dy dx, just like it's always been, no matter whether you're in parametrics or not. The slope is dy over dx, change of y over change of x. How much does y change compared to x? Well, we learned that from parametrics equals dy dt over dx dt. And dy dt is the derivative of y with respect to t. Derivative of tangent is secant squared. And dx dt, the derivative of secant, is secant t tangent t. So it's going to be secant squared over secant t tangent t. One of the secants cancel, and you're left with secant t over tangent t. Secant t is 1 over cosine t. Tangent is sine t over cosine t. You divide by a fraction, you multiply by the reciprocal, cosine over sine. The cosines cancel. You're left with 1 over sine of t, which is equal to the cosecant of t. We're trying to find the slope at t equal pi over 4. So since this is dy dx, we started out with dy dx. When we got all the way to here, dy dx is cosecant of t. The cosecant of pi over 4, plugging pi over 4 in there, is going to be 1 over the sine of pi over 4. The sine of pi over 4 is radical 2 over 2, which is 2 over radical 2. And when you rationalize, it ends up just being radical 2. And I do want to bring this by. I want you to realize that 1 over radical 2 is equal to radical 2 over 2. That's kind of helpful to know when you're dealing with trig values, that radical 2 over 2 comes from rationalizing the denominator of 1 over radical 2. So when you want the reciprocal of radical 2 over 2, it's really just the reciprocal of 1 over radical 2, so it's radical 2. So we've got our slope is radical 2, and our point is given to us right here, radical 2 comma 1. So x minus radical 2, which is x minus x1, and y minus y1 is going to be y minus 1, and then our slope m we found to be radical 2, so there's your tangent line using parametric.